Hello and welcome everyone to another video on limits. In this video, we are going to discuss about infinite limits and vertical asymptotes. So we say limit as x approaches a of f of x equals infinity if the values of f increases without bound as the value of x not equal to a approaches a. So which means, we have a function. So for example, there is a here. And then the function, when x approaches a, if the function increases without bound, like that, then we say that so we have a vertical asymptote here. So we say this one, we call it, okay, so limit as x approaches a, f of x equals infinity. That means when x is very close to a, the function goes to infinity. Similarly, it's true when it goes to the negative infinity. So when x approaches a, if the function is going to negative infinity, or if it decreases without bound, that means it goes to infinity, then we call it limit as x approaches a, f of x equals negative infinity. So let's look at an example. So if you remember in the last video, we did direct substitution to evaluate the limit. Also, we talked about if we get 0 in the denominator, then we can factor and simplify the expression and then do the substitution. Or we could also rationalize the expression by multiplying by the conjugate, usually in the case when we have the radicals. But if we get a 0 in the denominator, and if there's no way to factor and cancel or simplify the function, then we have to either use a graph or we have to use an analytical method. So those are the two things that we are going to see in this video. So the first example is we are going to use on the graph of this function to find the limit. So I already have drawn the graph. If you want, you can do that in your calculator, put the function and look at the graph. So here from the graph, so as x approaches 2, the function increases without bound, which means the function heads towards infinity. So that means from the graph, we can say that limit as x approaches 2 of x over x squared minus 4 squared equals infinity. Similarly, when x approaches negative 2 from both sides, we see that the function is decreasing without bound. So we write it limit x approaches negative 2 of x over x squared minus 4 squared equals negative infinity. So one more thing here, when the limit as x approaches a is infinity or negative infinity, or if the limit is infinite limit, when x approaches to a finite value, then we have a special line passing through x equals a, that is called the vertical asymptote. So in this case, this line, okay, and then this line here, these two lines are the vertical asymptote for that function. So the vertical asymptote for this function are x equals 2 and x equals negative 2. So just like the regular limit that we have seen before, the infinite limits could be one-sided. So for example, if you have a function such that, so let's say this is a, and then the function goes to infinity when it comes from the left, and then function goes to negative infinity when it comes from right. So if we have something like that, so the left limit, so limit as x approaches a from the left of f of x here is infinity. And then if we write limit x approaches a from the right of f of x equals, here it is negative infinity. So just like other regular limit, the infinite limit could be one-sided. When we approach from left and right, sometimes from both directions, the limit goes to infinity, sometimes it goes in the opposite direction. So this is similar to what we did in the previous videos, okay? So now this is what happens. So if the limit as x approaches a from the left is positive or negative infinity, or if as x approaches a from the right, if the limit is infinity or negative infinity, or from the both direction if the limit is either infinity or positive. So any of this condition, okay, if any of these conditions hold, then we have x equals a as the vertical asymptote for the function. Again, it doesn't have to be two-sided limit. Okay, we could just have one-sided limit going to infinity, other going to negative infinity, or both going to infinity, or both going to negative infinity. In any of those cases, if we just have one of these conditions, then x equals a is the vertical asymptote. Now let's look at this example. So we are going to look at the graph again, and then we'll find this limit. So the first one is, so again, we cannot do the direct substitution. Always in this case, when you're finding limit, no matter what function you're looking at, the first thing you want to try is try to plug it in and see if we can do the direct substitution. Okay, so here, finding limit as x approaches 2, if I plug in 2 here, I'll get 0 in the denominator, so which means I cannot do direct substitution. And there's no way that I can factor out and then cancel that and then simplify the function. So what I have to do is I have to use either graph or analytical method. We'll see analytical method in the next example. So here we are going to use the graph, okay? So as x approaches 2 from the left and also from the right, from the both direction, okay, the function decreases without bound, or the function goes to negative infinity. That means this limit is negative infinity. Now for the next one, as x approaches 5 from the left, so as x approaches 5 from the left right here, the function decreases without bound, or the function goes to negative infinity. That means this limit is negative infinity. Now as x approaches 5 from the right, okay, so when x approaches 5 from the right, the function increases without bound, or it goes to infinity. That means this limit is infinity. Now the limit as x approaches 5, if we look over here, the left hand limit is negative infinity. The right hand limit is infinity. So the left hand limit and right hand limit are not same. That means this limit does not exist. Okay, it's not infinity, it does not exist because it's not same from both the direction. Now we need to write the vertical asymptote for this function. Remember, even if one-sided limit exists, then we can say that a x equals a is the vertical asymptote. So here, as x approaches 2, we have a negative infinity as the limit. So that means x equals 2 is the vertical asymptote. Similarly, as x approaches from the left, as x approaches to 5 from the left, we have negative infinity, or as x approaches 5 from the right, we have infinity as the limit. So that means x equals 5 is also the vertical asymptote. So these two are the vertical asymptotes for this function. And then from the graph, we can verify that. So at x equals 2, we have this vertical asymptote right here. And then at x equals 5, we have this vertical asymptote right here. So that means we verify that from the graph as well. Now, the next question is, if we don't want to find those infinite limit from the graph, then how do we do that? So the way that we do is called the analytical method, where we don't need to draw the graph. We can just look at the function and then we can evaluate the limit, okay? So again, the first thing that you are going to do is if I plug in, so we are trying to find the limit as x approaches 3 from the left. So if I plug in 3 here, I'm going to get a 0, so direct substitution does not work. So what we do here is we are going to do an analytical method, and this is how we are going to do it. So for this one, as x approaches 3 from the left, so if we draw a number line, okay, so for example, we have a 3 here. When x approaches 3 from the left, right like this, the x are the numbers right here on the left of 3. They are very close to 3, but they are to the left of 3. That means x is less than 3, which gives us, if we subtract 3 from both sides, we get x minus 3 is less than 0. Now, it means x minus 3 is a number which is very small number because x and 3 are very close to each other, but it is a number which is less than 0. That means it's a negative number. Now let's go ahead and find the limit. So what we are going to do now is limit as x approaches 3 from the left of x minus 1 times x minus 2 divided by x minus 3. Now this is how we are going to analyze the limit, okay? So we are going to find the limit. So what we do here is, so for the denominator, we know that x minus 3 is a number less than 0 and it's very, very small number. So what we are going to write is, we are going to write this x minus 3 is a negative number, okay? So it's a negative number and it's really small, so we write it approaches 0. Now if you look on the numerator, if we plug in 3, you get 3 minus 1 is 2 times 3 minus 2 is 1, which is 2 times 1 equals 2. So it's not exactly 2, but the number in the numerator is very close to 2. It's approaching to 2 and it's positive. So it's a positive number and approaches 2. Now we are dividing a number, finite number. So the numerator is a finite number, okay? Finite number. We are dividing a finite number, positive finite number, by a negative number, which is very, very close to 0, which is almost 0. So when you divide a finite number by a really small number, you will get a huge number. But in this case, we are dividing a positive by negative. So we are dividing positive number by a negative number. That means we get a negative number. But you're dividing 2 by a small number, that means we get a huge number. And then when we are talking about limit, that huge number, it gets bigger and bigger and bigger, so that becomes infinity. Now, as a whole, it's a big number, but it's a negative number, so that means that is a negative infinity, or the function as x approaches 3 decreases without bound, okay, from the left. So that's how we do that, okay? Now, similarly, let's go ahead and find the limit of that function when we approach to 3 from the right. So let's do this, and then let's go ahead and find this limit from the right, okay? So when, again, let's draw that number line, and then when x approaches 3 from the right, that means the x are the numbers right here on the right of 3, okay? So when x approaches 3 from the right, that means x are the numbers which are always greater than 3. So x is always greater than 3, which means if we subtract 3 from both sides, we get x minus 3 is greater than 0. So x minus 3 is a small number because x and 3 are very close to each other, but it is a positive number. Now we do the same thing that we did for part A. So we are going to write limit as x approaches 3 from the right of x minus 1 times x minus 2 divided by x minus 3 equals. So now let's again do the same thing that we did earlier. So what we are going to see is x minus 3 is a really small number because it's close to 0, but it is positive. So we are going to write this is a positive number close to 0, or you can write which approaches 0, okay? And the numerator is a number which is close to 2. So the numerator is also a positive number which approaches 2. Now what we are doing is we are dividing a positive number by positive number, so we are going to get the result as positive, but we are dividing a number which is close to 2 or almost 2 by a really small number close to 0. That means our quotient, our result is really large, and then as we make that x very, very close to 3, that function goes to the infinity, or the value of the limit goes to the infinity, so we get infinite limit here. Now for the third part, so we saw that this is the left hand limit, This is the right hand limit. Left hand limit is negative infinity, and the right hand limit is positive infinity. That means this limit does not exist. Now, the next thing that we are asked to find is the vertical asymptotes for that function. So the vertical asymptote are, we just have one vertical asymptote, which is x equals 3, because we got that infinite limit. And then if we have to verify that using a graph, then you can put this in your calculator and graph the function. But here clearly, I already have the graph here, and you clearly see that we have a vertical asymptote here. And as x approaches 3 from the right, function goes to infinity, which is this one. And then as x approaches 3 from the left, the function goes to negative infinity, which is this one. Now, this is a question where I want you to try on your own. So you can pause the video, try the problem, and then you can resume the video and then check your work. But we are going to do it now. So the first thing is we are asked to find limit as x approaches -1 of f of x. So let's go ahead and do this. I cannot substitute that, but it looks like I can factor and simplify. Let's try that, okay? So limit as x approaches -1 of, so if we factor the numerator, we are going to get x plus 3 times x plus 1 divided by denominator, will get x plus 1 times x minus 1. Now we cannot plug in -1 because we'll get a 0, but remember in this case it looks like we can go ahead and cancel out these two factors, and then we get limit as x approaches -1 of x plus 3 divided by x minus 1. Now, if I plug in -1, I'm not going to get a 0 in the denominator. So that means I can do direct substitution. So if I plug in -1 in the numerator, I'll get 2 divided by -1 minus 1 is -2. And then I get a -1, which is a finite limit. Now, one thing, so -1 is not in the domain of this function, but we got a limit. So if we look on the graph here, we see a hole at x equals -1, we have a hole. So x equals -1 is not in the domain of the function, but still the limit exists, because when we approach to -1 from both left and right, the function approaches to a value of -1. Okay, and then we don't have a vertical asymptote here because the limit is not infinity. Okay, the limit is not infinite limit. So that means we don't have a vertical asymptote. But now from here, you need to understand that if we are able to cancel the common factor and evaluate the limit when we have 0 in the denominator, those are the points, those are the x values where we have a hole. Okay, when we get the infinity as the limit, those are the x values where we have the vertical asymptotes. So something that you need to keep in mind. Okay, so let's look at the next example here. So for this one, now for this one, we already have simplified the function. So we'll just take this one and we'll use this. Okay, so we are going to find limit as x approaches 1 from the left. Again, we need to make that number line because we cannot substitute 1. If we do that, we'll get a 0. So we have to do this analytically. So that means here we have 1. When x approaches to 1 from the left, x are the numbers which are less than 1, and that gives us x minus 1 is less than 0. So we're exactly going to do the same thing that we did for the previous question. So limit as x approaches 1 from the left. So instead of writing f of x as this one, I'll take this simplified version and I'll take this one and put it here. Okay, so x plus 3 divided by x minus 1. And then now we cannot plug it in. So using this analytical method, I know that x minus 1 is a small number less than 0. So it's a negative number. Okay, so it's a negative number close to 0 or approaching to 0. In the numerator, when I plug in 1, I get 4. So it's a number, positive number close to 4. Now, if you divide a number 4, a finite number, by a really, really small number, you'll get a huge number. So we get infinity, but we have positive divided by negative, so we get negative infinity. So that's the limit for when x approaches 1 from the left. Now, similarly, for the right one, x is greater than 1, so it means x minus 1 is greater than 0 or a positive number. So now if we have to do that limit, sorry, if we have to do that limit, so we are going to do this. So this limit equals limit x approaches 1 from the right, and then we'll take the same function, the simplified version. Now in this case, numerator is a positive number close to 4 divided by, close to 4, divided by the denominator is also a positive number close to 0. Means it's almost 0, very, very small. Now again, when you divide a number, finite number by really small number close to 0, we get infinity. In this case, we divide positive by positive, so we get positive infinity. So we got the positive and negative infinity as x approaches to 1 from right and left. So the limit as x approaches 1 does not exist because it goes to two different directions, but still we have the vertical asymptote. So the vertical asymptote for this function is x equals 1, okay? And then from the graph, we can verify that at x equals -1, there is a hole, so this limit, and then at x equals 1, we have this vertical asymptote, which is this limit, okay? That's all for this video. I'll see you again in the next video. Have a great day.